All right, so today we're going to talk about vectors, and the example I like to use to introduce this idea of vectors is with planes and wind. Okay, so let's suppose that a plane is traveling 300 miles an hour and it's going straight north. Okay, and the wind is don't write this down, but just to give you an idea. So the plane is going in this direction, and it's going straight north, and it's going 200 miles an hour. 300 or whatever I said, so 300 I guess. It's going 300 miles per hour. And then there's a wind coming from the east, okay, so blowing from east to west, and it's pushing on the plane. So if the plane does nothing, and it's getting hit by wind like this, then what's going to happen is the plane is actually going to move in this direction. So what we can imagine is the wind comes in like this, and the plane actually starts moving in that direction. So you can probably imagine that, right? Even if it's only a 50 mile per hour wind, it's still going to push the plane off of the course of straight north. Okay. So to represent that situation mathematically, we use these things called vectors. Okay, and vectors are used to represent anything that has a magnitude and a direction. So in our plane example, the magnitude of the plane's velocity is 300 miles per hour. The magnitude of velocity is speed. Okay? It also has direction. The plane has direction. The plane is going straight north. So any situation in which there's a magnitude, speed in this example, and direction, straight north in this example, we can represent that with a vector. So they're incredibly useful in all kinds of applications in science and physics and other contexts. Okay? So let's formally define it right here. Vectors are a mathematical representation of anything that has magnitude and direction. They're represented by an arrow or a ray, if you remember from geometry. Okay, so they're represented by an arrow. The notation here that looks like A comma B, but it's not a point, it's got these two arrows pointing off to each side, is used to denote the vector whose initial point is located at the origin and whose terminal point is located at AB. Okay, so this is where you want to start writing. So if I start the vector here, and it goes out to point AB. So out here somewhere is the point A, comma, B. Okay. That vector we would call AB. Okay, and we would write this vector, or A, comma, B. We'd write that vector like this, A, comma, B. And it starts at initial point, the origin, and it ends at the terminal point, A, comma, B. And this form right here, this with the arrows, is called component form. And it's written that way, or it's called component form, because if you break this vector into its left, right, and up, down parts, those are called its components. So this horizontal distance would be A, and the vertical distance here would be B. Okay? So each component, each part of the vector, the horizontal part and the vertical part, is A, horizontal, B for vertical, and it's written as A, comma, B. Okay. Two vectors are equivalent if they have the same length and point in the same direction. So I could take this vector here, and I could move it anywhere in the plane, so in the XY plane. So sometimes in fact, lots of times, it's useful to start it at the origin, but we could start it anywhere. So I could move this vector up to here, and it's no longer starting at the origin, but imagine that was the same length. So but this vector is equivalent to this vector in that they have the same direction and that they have the same magnitude, the same length. Okay? So we will talk a little bit more about vectors in other examples, but the big idea here is anything that has magnitude and direction can be denoted by a vector. The length of the arrow represents the magnitude. So if we go back to the plane example, it was 300 miles per hour. That vector would be shorter than if the plane was going 400. We would represent that with a longer vector. Okay? All right, so let's do this head minus tail rule. Okay, so if an arrow has initial points at x1, y1, and terminal point at x2, y2, remember, initial point is where the vector starts, terminal point is where the vector ends. It represents the vector given by this, x2 minus x1, y2 minus y1. So we can sketch that out. If you take any vector in the plane here, so if you started here at -2, 2, and you draw it to 2, 6. Or in fact, let's just let that be any, well, no, that's fine. So we'll go -2, 2. And this is 2, 6. So that vector right there, we can write that as the vector that starts at the origin. In other words, the one that is in component form that we just talked about. We can write that by taking x2 minus x1, y2 minus y1. That's the component. So if we call this x1 and y1, we call this x2 and y2, then we can write this as, so let's see, x2 minus x1, that'd be 2 minus the -2, that'd be 4. So we should write this, so we'll write the vector as 4, comma, and then we'll take y2 minus y1, which is 6 minus 2, so 4, comma, 4. Okay, that's the vector, and we could draw that at the origin if we wanted. It would just be go over 4 and up 4. So that vector would look like that. Okay? You can see that vector is the same length, it's the same direction, it's an equivalent vector, but it's drawn at the origin, and we can write it in its component form. Okay? Now you don't have to use the fancy formula there if you don't want to. You can just count. So what is the horizontal component? Well, it goes to the right 4. And then what is the vertical component? Well, it goes up 4. Boom, there's your components of the vector. Okay, let's show that these two vectors are equivalent. RS and PQ. So let's draw R as at -4, 2. So -4, comma 2. S is at -1, 6. -1, 6. So that's here. So that's R, that's S. Okay, and then PQ is from 2, -1, so over 2, down 1. That's point P to Q, which is at 5, 3, so 5, 3. Right, and so that vector, we want to show that it's equivalent. So in other words, we need to find the components of each one. So vector RS, when we write a vector, lots of times on a sheet of paper, when it's printed in the book, it would be bold, but it's hard to bold with your pencil or with a marker, so we draw an arrow over the top of it to denote that it's a vector. So we want to find the components of RS. So we can use the formula, or we can just count. So we go from -2 over to -1, that's 3. And then it's up from 2 to 6, so up 4, so 3, comma 4. And then we can come over here to PQ, and we can find the components of this vector in the same way. So we start here at +2, and we go over to 5. All right, so the components here of PQ are 3, and then from -1 up to 3, that's 4. So that shows that they are in fact equivalent vectors. They have the same length, and they have the same direction.